Okay, so thank you very much. Okay, I would like to thank very much for giving me a chance to have a presentation at this very nice international workshop. So today I would like to talk about auto-frequency pairings in topological superconductors. So the contents of my talk is as follows. First, I would like to introduce what is surface Andreev band state and relevant auto-frequency pairing. So actually, such a group has a nice presentation. I will skip the very introductory part of what is auto-frequency pairing. But I'd like to mention about the history of study of auto-frequency pairing. So one of the stream of the study is how to seek, how to generalize, how to realize the so-called bulk state of auto-frequency superconductor. It's a really difficult problem. So actually, it's relevant to difficult many body problem and continues this activity. And whether really a uniform auto-frequency superconductor is possible or not, it is not clarified yet. On the other hand, auto-frequency pairing amplitude or pairing correlation can be generated by the so-called induced symmetry breaking from standard even frequency well-known superconductor can be described by mean field theory. Actually, there are several routes to generate auto-frequency pairing. So starting from, for example, even frequency spin singlet to even parity case by translational invariance breaking. So auto-frequency spin singlet auto-parity pairing can be generated. And also spin rotational symmetry is broken. So then from ESE pairing, auto-frequency triplet even parity pairing can be generated. And it is actually discussed in many works, first discussed by Effetov and Borkov and Buzdin, Bergeret and Eschrich. Many important works has been done in the context of spin ferromagnet superconductor junction. And also recently, multiband superconductor is a generation of auto-frequency pairing is discussed, starting from Brakshaw and Baratsky's original work, and Asano and Kanatsugi and many works, many activities. So then let's discuss very basic point. Even in well-known Bogoliubov-Dujan equation, but still it includes auto-frequency pairing implicitly, and spatial change of the pair potential, translational symmetry breaking, can induce auto-frequency pair amplitude simply from conventional even frequency superconductor, and especially in the presence of Andreev bound state, the magnitude of auto-frequency pairing is enhanced. And so we clarify this issue, and actually, let's look at the surface state of D-wave superconductor. It was discussed in the context of high TC cupulate, and this flat band dispersion is really relevant to auto-frequency pairing. And it's an experiment by our collaborator, Professor Kashiwaya. And actually, if we calculate the pair potential near the surface of D-wave superconductor or triplet P-wave superconductor, pair potential is generally suppressed, and eventually, auto-frequency pair amplitude is generated. In this case, since the bulk parity is even parity superconductor, auto-frequency, auto-parity singlet pairing is generated. And eventually, we expect such kind of huge zero energy state. And also in P-wave case, in this case, auto-frequency spin triplet pairing is generated, and also zero energy peak is, appears. And so it can be, interpreted as follows. So surface Andreev bound state is actually generated from the sign change of pair potential like that. And then we expect zero energy surface Andreev bound state. And eventually we expect auto-frequency pairing amplitude. Both have similar energy dependence, and both are localized at the edge with similar energy dependence. So this is one of the basic points. So then let's look at how it is relevant to topology. Topological nature of superconductor. So there are so many works about topological superconductivity, but I would like to mention about very basic, very simplified model. So 2x2 model. Even such kind of very simplified model, so we can discuss a topological structure of this Hamiltonian. So let's define winding number like that, and xi is the kinetic energy, and delta is the pair potential written in momentum space. So then we can define theta parameter. And if we integrate theta from -pi to pi, we can define so-called winding number. So this is a starting point. And actually, Professor Sato or Yada-san has clarified that winding number can be described like that. So it is after some simple manipulation, winding number becomes something like topological invariant defined in bulk Hamiltonian, and signature delta is a sign of pair potential, and signature of this quantity is a simple signature of Fermi velocity on the Fermi surface. And if we consider a very simple Fermi surface like that, and concentrating on the crossing point P and P prime, so then we can define velocity and also a pair potential, sign of pair potential, and only the signature of this product determines everything, and we can define winding number. On the other hand, this very simplified Hamiltonian has a non-trivial structure, so-called chiral symmetry, and we can, from the bulk edge correspondence, there exists a gapless surface Andreev bound states on the edge only when integer W1D is non-zero. And index theorem, so-called index theorem, is satisfied here, and winding number becomes a, how to say, number of zero energy state, where the eigenvariable sigma y is unity and minus unity. This difference, it just corresponds to winding number. So let's apply this theorem to actual high TCQ plate and P-wave superconductor. In D-wave case, so we check this relation, but we want to emphasize this point. This winding number has a sign change when Ky is positive or Ky is negative. So this is an important point when the direction of quasi-particle around here is positive or negative. Sign of winding number changes. On the other hand, for spin triplet case, this sign change never occurs. So it is always, for example, in this case, minus unity. So how this qualitative difference appears in the actual condensed matter physics? This is an important issue. So for this purpose, so-called anomalous proximity effect is very suitable. So actually, we have clarified with, in collaboration with Sasha Golubov. So if we consider spin triplet superconductor, and we attach diffusive normal metal, odd frequency spin triplet S-wave pairing, so-called Berezinski pairing, is generated in diffusive normal metal. And the anomalous proximity effect is due to odd frequency spin triplet S-wave pairing, and it shows a very exotic nature of local density of states by contrast to well-established spin singlet S-wave superconductor studied in mesoscopic superconductivity. In that case, density of state should have a, how to say, gap-like structure at zero energy. But in this case, this anomalous proximity effect tells us that local density of state has a peak-like structure. And so zero energy peak appears in the local density of states. And also paramagnetic Meissner effect is predicted. And actually such kind of tendency has been observed in topological insulator superconductor junction recently, and also perfect resonance of conductance at zero voltage. So essentially equivalent to the tunneling through Majorana fermion discussed by Ikegaya-san yesterday. So then let's go to so-called spectral bulk edge correspondence. We have clarified very recently with Dr. Tamura and Hoshino in Saitama University. So let's talk about what is spectral bulk edge correspondence. So actually, I have explained up to now, we should expect some odd frequency pairing at the edge, as far as we are considering topological superconductor. But we know that this edge state is relevant to edge state, is relevant to bulk topological number, but we do not know exactly how odd frequency pairing is relevant to bulk quantity. So, but we have clarified that if we define winding number extending to C number, no more the integer, but if we calculate winding like number, some kind of C number, then the correspondence exists. So I would like to mention about this, and by applying this theory, so we can classify the, how to say, analytical nature of odd frequency pairing more in detail. So let's go. So odd frequency pairing. So total amount of induced odd frequency pairing can be decomposed into two parts. First one is singular part, so-called singular part, which is proportional to inverse of Z. These are frequency. So then this number W is integer, and only when a topological number is defined in the bulk, this term appears. On the other hand, This term always appears in every odd frequency pairing, odd frequency pairing amplitude. And the interesting point is that this number chi diverges at the topological quantum critical point. So I would like to mention about Tamura-san's work from now. So we know that there is a good correspondence between bulk topological number and zero energy edge mode. So from bulk boundary correspondence. On the other hand, we have clarified, and other works by Asano-san or Higashitani-san mentioned that zero energy surface edge mode is closely relevant to odd frequency Cooper pair arises at surface. So how about the relation? Are there any direct relation between bulk topological invariant and odd frequency Cooper pair arises at the surface? So we find a relation between the topological invariant and the odd frequency S-wave Cooper pair for now. So let's briefly mention what Tamura-san has done. So he has first calculated the odd frequency pairing amplitude accumulated at the surface, and independently he calculated the extended version of the winding number and checked some relations. And after they have, we have submitted the paper. This relation is mathematically proven by Dr. Daido and Professor Yanase later. So then let's apply this interesting relation to very well-known model of one-dimensional topological superconducting hybrid junction system. So Hamiltonian of this system has been explained many people in this workshop. So I will skip it. We assume Zeeman field and also spin-orbit coupling in nanowire system. So of course, Myron fermion appears as end state in topological phase. So let's look at how topological transition occurs and how odd frequency pairing appears in this very interesting system. So then let's look at this situation. In this case, magnetic field chosen like that. This is a transfer energy. And in this marked region, red marked region and green marked region, we can define a winding number like that. And here is a fermion level. And then by increasing the magnitude of magnetic field, then this regime changes into topological and also changes again into non-topological. So it's interesting to clarify the induced odd frequency pairing for various phases. So then let's look at that. So here is a, how to say, boundary induced odd frequency pairing. And it's a quantity defined in bulk. And actually we have checked quite good high accuracy that the new bulk boundary correspondence checked numerical. So because this value and the difference between these values are very, very small as seen from this graph. So then let's go to next part. How about the frequency dependence of induced odd frequency pairing? So let's look at curve, this red curve or orange curve. So in this region, it's how to say, odd frequency pairing behaves almost linear around omega equals 0. So it's a trivial phase, and induced odd frequency pairing is proportional to omega. On the other hand, in topological phase, it has a divergent behavior like that. So then this is a clear difference. So in topological phase, odd frequency pairing amplitude is inversely proportional to omega. On the other hand, trivial phase, it is proportional to omega. So then F can be expanded by omega as follows. So F becomes like that. Okay, so here W is integer and chi is a real number. How this behavior, how this value behaves, it's quite interesting point. So then let's more in detail. So we call it, so this is a singular part and this is a regular part. And also singular term corresponds to topological phase, and regular term corresponds to non-topological phase. So let's go to the winding number defined like that. So actually in trivial phase, winding number defined like that is 0, and in topological phase is, of course, it's an integer. So at the same time, we look at chi, which is a coefficient linear term of omega, how chi behaves. So as seen from here, chi first increases by closing the topological critical point, and just in a topological quantum critical point, this value diverges. And also from topological, closing from topological phase, so first it is almost 0, and also it's diverging. So the critical region is very, very narrow in topological phase. So chi can be regarded as a kind of susceptibility. So this is an interesting nature. So then let's go to next one. Are there any quantities, physical quantities, which behaves similar to W and chi respectively? So let's look at first the charge conductance and charge conductance at especially EV equals 0. So in trivial phase, the charge conductance behaves like that, and EV equals 0, it is almost 0. On the other hand, in topological phase, it becomes like this. Of course, it is completely quantized. Yes. So then it corresponds, this difference just corresponds to the difference of winding number W. So it's a charge conductance, trivial phase and topological phase. And so it just corresponds to that. So the winding number W appearing with the, how to say, analytical expression of W appearing with the, how to say, omega dependence of F. So W, the value of W corresponds to the charge conductance at 0 voltage. So like that. Okay. So sigma EV equals 0 and W have the same information. On the other hand, how chi is relevant to any physical quantities? So actually, if we make a second derivative of charge conductance, the behavior of second derivative of charge conductance and chi is quite similar. And so Fi omega and sigma EV have a similar information. And yes, chi has a, like this correspondence. Okay, so then let's go to some summary of this part. So we consider, for example, one-dimensional system, effective one-dimensional system, which is a chiral symmetric system. And of course, there is a bulk boundary correspondence as far as we are looking at zero energy state. And we have a newly derived spectral bulk boundary correspondence, which connects directly from bulk C number to something like surface-induced amount of odd frequency pairing amplitude. So from this viewpoint, so odd frequency Cooper pair is really relevant to topological superconductor and especially edge state, so Majorana fermion. So then the summary of this part, so we found the relation between the extended winding number and the induced odd frequency pairing amplitude, and odd frequency pairing can be decomposed into singular part and regular part, and the singular part appears only in topological phase with zero energy surface and F bound state. And the coefficient of regular part of odd frequency pair amplitude diverges near the topological transition. So that this is a relation we have derived. And so odd frequency pairing is an indicator of topological superconductivity. And so W is an integer I have already explained, only in the topological phase, and chi diverges at topological critical points. Okay, so the remaining part, I would like to mention about the thermoelectric detection of surface and F bound state. Very recently, we have joined this discussion. So this work mainly studied by Sabanda in Finland in collaboration with Pablo Biruset. Now he becomes a professor in Madrid. And so we collaborated, our group joined collaboration with them. So the result is very clear. So now we look at the charge conductance triggered by temperature dependence between ferromagnet and superconductor. So up to now, such kind of study has been done in conventional superconductor, but in the presence of zero energy surface and F bound state, the sign of induced current is reversed. This is the main message. So then the time is not so much. I would like to briefly mention what we have done. So this is actually such kind of activity. Large thermoelectric effect has been studied in ferromagnetic superconductor junctions, and it is reported that Seebeck coefficient is much larger than the values of normal metallic structures. So my motivation is very simple. So it is interesting to study thermoelectric current in unconventional superconductor junctions with surface and F bound states. And also we would like to clarify the role of induced odd frequency pairing. So then I will skip this one, so that electric current in the junction can be written like that, and the temperature difference is important. Of course, temperature difference triggers a non-zero current, but in that case, some kind of asymmetry of conductance around zero energy is really needed. And if we look at just at V equals 0, the electric current can be expressed by purely Andreev process. So Andreev reflection, by evaluating Andreev reflection, we know electric current in this junction. So then let's apply to D plus IS wave pairing state. It's in some sense toy model, but it's discussed in the context of Q-plate before. And it's a good text model because if we skip this term, so it reduces to purely D wave case, topological state. And if we drop this term, then it reduces to completely trivial S wave case. And between these two, so then the surface Andreev bound state appears, but it is no more topological because chiral symmetry is broken. So how this systematic change occurs appears in thermal electric effect is a quite good model. So then let's calculate it. So first look at the charge conductance. So charge conductance changes systematically by including delta this value, delta 1. So if delta 1 is unity, it's a purely D wave case. It should be, how to say, symmetric without x equals 0. So x is an exchange energy in ferromagnet, but we introduce x and include delta 1. The charge conductance behavior changes systematically because zero energy state split and due to S wave component. And also this difference appears, of course. So this difference, sigma E minus sigma minus E, the non-zero sigma E minus sigma minus E generates a non-zero thermoelectric current. And so the important point is that if in the presence of zero energy state, this peak appears just zero. And this systematic change very similar to delta F. So then the sign of thermoelectric current changes due to the position of peak. And if the position of zero surface Andreev bound state peak just almost located at zero energy, then sign change occurs and thermoelectric current, the sign of thermoelectric current is reversed. So this is the idea. And actually we have applied it for px wave, dxy, or chiral p wave like that. Then as compared to S wave, D wave, or chiral D wave case, the sign of thermal electric current is completely reversed. Okay, so then finally, I would like to mention the role of odd frequency pairing. Actually, this thermoelectric current can be expressed by Andreev process. And if you carefully look at decompose into this Andreev process, it can be written like that. It's a, how to say, a product of even frequency pairing and odd frequency pairing. But first term disappears after angular integral because the parity of this term is odd as a function of theta, injection angle. On the other hand, latter term survives. So it's interesting that this is a mixture of even frequency spin singlet to even and odd frequency triplet to even. So mixture of even and odd and mixture of singlet and triplet. Then after averaging, how to say, momentum direction, this term survives, and this term contributes to the non-zero thermoelectric current. So the mixture is very important, and of course, it means that odd frequency pairing makes an important role to generate new type of thermoelectric current. So then I would like to summarize this part. So thermoelectric effect at V equals 0 is entirely due to Andreev process, and we have demonstrated that the thermoelectric current is reversed in the presence of low energy surface Andreev bound states at the surface superconductor surface, and the thermoelectric effect only arises if even and odd frequency Cooper pairs coexist in mixed singlet and triplet states. And we have actually published it in archive number. And so I finally send you a message. So odd frequency pairing is enhanced in the presence of surface Andreev bound states and the topological origin of surface Andreev bound state. If we focus on this topological origin, so nodal superconductor like high TC Q-plate can be regarded as topological superconductor, and also anomalous proximity effect by odd frequency triplet S-wave pairing, and Majorana fermion accompanies odd frequency pairing. And so we newly found spectral bulk boundary edge correspondence. And we have found new type of odd frequency, new type of thermoelectric current, Zeebeck effect by surface Andreev bound state and odd frequency pairing. I would like to thank organizer for giving me a chance to have a presentation. Thank you very much.